Hello everyone, today, or at least this week, we're going to be talking about prime and composite numbers. And so, quick definition, prime number means that it's only divisible by itself and 1. Composite numbers mean that they are divisible by multiple numbers other than 1 in itself. So for example, 10 is a composite number because it is divisible by 10, 1, 2, and 5. The other hand, 13 is not a composite number, it's a prime number because it's only divisible by 13 and 1. And 1 is a special exception because it's neither composite nor prime. Alright, so I'm going to start this off. In this lecture, we only have one problem, that's problem 1. But before I go into problem 1, I'm going to discuss the divisibility rules. And when we get into advanced number theory a few weeks later, most of these rules will start to make more sense. So our divisibility rules for 2. It is divisible by 2 if the last digit is even. And so the even numbers are 0, 2, 4, 6, and 8. So the last digit is one of these digits, then that means it's divisible by 2. And that's pretty intuitive, I think. If it's divisible by 3, that means that the sum of all its digits is divisible by 3. So for example, if you have a number like 396, for example. Is that a little bit too obvious? Alright, how about this? 252. So 252 is divisible by 3, and we know that because 2 plus 5 plus 2 is equal to 9, and 9 is divisible by 3. Now we can test this out by actually dividing 252 by 3. So that's equal to so that 252 divided by 3 is 84. So it is divisible by 3. And when we get into modular arithmetic, you guys will actually have a proof for this rule and why it works. For now, I guess I would just say try to, accept that it works. Or you can go out and, search on the internet and try to figure out yourself. I would always encourage that. Alright, it's divisible by 4. A number is divisible by 4 if the last two digits is divisible by 4. So and the reason why this works is because 100 is divisible by 4. So if you have a number like 25892, we know that 25,800 is divisible by 4 because 100 is also divisible by 4. So 25800 is equal to 2,258 times 100, and this is all divisible by 4. So we established that this part is divisible by 4. We just need to make sure that 92 is also divisible by 4. And we'll see that it actually is. 92 divided by 4 is equal to 23. Yeah. So for divisibility by 4, check the last two digits. Divisibility by 5, last digit has to be either 0 or 5. Divisibility by 6, it has to be divisible by 2 and 3. Because if it's divisible by 2 and 3, then 2 times 3 is 6. If it's we don't actually have a good divisibility rule for 7. I would just say straight up divide it. Divisibility rule by 8, last 3 digits has to be divisible by 8. And the same reason for this rule applies to, for the rule of 4 applies to the rule for 8. And the reason for that is that 1,000 is divisible by 8, right? So we know that, if we have if we have a question, if we're trying to figure out divisibility for 2,508.92, we know that 8 is divisible by we know that 1,000 is divisible by 8, so we can split this up into 25 times 1,000 plus 892 divided by 8. And then you can, split that up. You can actually divide this, so this is just 25 times 1,000 divided by 8 plus 892 divided by 8. And we know that this is all divisible, so we just need to figure out if this part is divisible. And for this part, I would just say straight up divide it. Divisibility by 9. And the rule for that is it's kind of the same as the rule for number 3, except it's that the sum of digits is divisible by 9. And then we have divisibility rule for 10, which is that they have to be divisible by both 2 and 5. So 10, or you can just, look at the ending. If the last digit is a 0, then it's divisible by 10. So last digit is 0. So these are divisibility rules for the numbers from 2 all the way up to 10. I've skipped over 7 because there really isn't a good way to, there isn't really a good divisibility rule for 7. Although a special case is 11. 11 is the next prime, so I'll also go over that divisibility rule. And for other ones like 13 and 17, I would say you would have to just divide it. But alright, divisibility rule for 11 is, I'll use another, this one's running out of ink. Divisibility rule for 11 is a little bit weird. And, alright, so let's say that you have a number like 121 times 11, and I'm gonna like multiply this out, and then I'll try to explain why the divisibility rule works. So 1 times 1 is 1, 1 times 2 is 2, 1, 1, 2, 1, 1, 3, 3, 1. So the rule for this is that you should add up every other number, so add up this number and this number, add up this number and this number, and then you need to subtract them. If the number that you get is divisible by 11, then that means that the number itself is divisible by 11. So if I do this problem, it's 1 plus 3 minus 1 plus 3, which is equal to 4 minus 4, which is equal to 0. And 0 is divisible by 11. 0 divided by 11 is 0. So we know that this number is divisible by 11. The reason why it works is like sort of how we multiply this out right here. So if I just use letters for this, you would find that if I have A, B, C times 11, I would have, and this is just an example, you can multiply it out by a larger number like A, B, C, D, E. I'm just starting with A, B, C in the beginning. We would have C, B, A, C, B, A. So you would get something that looks like this. The first digit is A, the second digit is A plus B, the third digit is B plus C, and the last digit is C. So you would see that if you add up this digit and this digit, you would get A plus B plus C. If you add up this digit and this digit, you would get A plus B plus C. Add them together, subtract them, it's 0, divisible by 11. And this isn't like a formal proof, right? This is just me trying to explain some of the intuition behind this rule so that it's easier for you guys to remember it. But I would suggest that you try this out with bigger numbers, and perhaps, don't multiply by 11, multiply by 121, which is a multiple of 11. Anyways, this is just the basics of the divisibility rules, although we are finally going to move on to our first problem. And our first problem is Find the prime factorization of 123,420, 123,420. 123,420. Well, off the bat, you just see that's divisible by 10. There's a 0 at the end, so we change that into... Well, I'm going to draw a factorization tree. 1, 2, 3. Oh. 12,342 times 2 times 5. Alright, when you look at this now, we know that it's also divisible by 2. So let's divide it by 2. We get 2 times 6, 1. We get 6171. And now what we can do here is use some of our divisibility rule. For example, let's test if it's divisible by 3. We would have 6 plus 1 plus 7 plus 1 is equal to 14 plus 1, 15, which is divisible by 3. So let's divide it by 3, and we get 0. 2,057. Alright, so we know that's not divisible by 9 or 3 anymore. So what we can do here is what we can notice here is that 2 plus 5, so this digit and this digit, minus 0 plus 7, or this digit and this digit, is equal to 0, which is divisible by 11. So we can divide this by 11. And we get 187. Alright, and what else can we do with this? Oh, well, you might notice it's divisible by 11 again, because 1 plus 7 is 8, 8 minus 8 is 0. So let's divide this number by 11. We get 11 here, we get 1, and then 77, so we get 17. And this is the complete prime factorization of this number. So if we take all of our numbers, be mindful that we don't actually miss anything. We have 2 squared times 3 times 5 times 11 squared times 17. And yeah, I think it might also be helpful if you guys remember the list of primes, perhaps all the way up to 50, because you're not going to get anywhere by trying to factor out 17. Oh yeah, also here's an example of the fundamental theorem of algebra, and that states that every number has a unique prime factorization. So the prime factorization for 123,420 is 2 squared times 3 times 5 times 11 squared times 14. And you'll see that in future videos, particularly number theory problems that involve factors. It's very useful to be able to find the prime factorization of something. Alright guys, thank you guys for watching. In the next video, we're going to go over prime numbers, more prime factorization, greatest common divisor, least common multiple. See you guys next time.